The operator theory of everything, 5 codes, 1 cosmos, is a provocative framework, blending mathematical rigor with philosophical insight. It suggests self-adjoint operators in the 5 codes can unify understanding across fields, identifying blind spots by analyzing missing principles. This framework is abstract and conceptual, not a standard theory in mathematics or physics, which may raise skepticism among traditional researchers. The connection to over 50 fields is ambitious, and the lack of direct empirical evidence for some applications could be debated. However, its interdisciplinary approach aligns with emerging trends in systems science and complexity theory, offering a novel lens for understanding. So buckle up for the episode. This is SpaceTime Cafe, episode 24.
Welcome back to the deep dive.
We're broadcasting live from our brand new SpaceTime Cafe studio right here in Austin, Texas.
We are super pumped up, ready for what feels like an epic journey today.
Definitely.
And look, to all of you out there who've joined us on this adventure through our previous 23 deep dives, your consistent support, your incredible curiosity, your fantastic questions, it truly means the world to us.
It really does.
Thank you for making this show what it is.
Seriously, your engagement is the fuel that keeps us going. And today, we are indeed diving deep again, pushing into some truly profound territory. We're tackling a puzzle that has mystified some of the greatest minds in physics.
You mean like the renowned physicist Eugene Wigner?
Exactly. His famous phrase, the unreasonable effectiveness of mathematics.
Ah, yes. It's such a perfect way to capture that feeling, isn't it? You think about it. These abstract mathematical ideas, concepts born purely from human thought, from logic and, well, imagination.
Pure thought stuff, absolutely. Things that could, in theory, exist only on paper or just in our minds.
Right. And yet somehow they are incredibly, almost mysteriously good at describing the physical world, predicting its behavior with just astonishing accuracy. It's like math isn't just our tool.
It's more like it's the very language reality itself is speaking.
Yeah. It feels unreasonable, doesn't it? How can something so abstract align so perfectly with the concrete universe?
It does suggest a deeper connection, maybe a fundamental blueprint,
It's incredibly profound when you stop and really ponder it. And if you were with us for Deep Dive 23, our last one, you might recall we started scratching the surface of why that might be.
We did. We explored that fundamental question of why the universe is stable at all, why things don't just fall apart.
We truly dug into that core idea, stability, through a profoundly fundamental concept called self-adjointness.
Right. We talked about how it's not just some mathematical property, but something maybe more like an ontological principle.
Not merely a description, but something that defines the very frame of reality, a sort of bedrock requirement for existence to even hold together, to be comprehensible.
Yeah, we framed it as the cosmic guarantee of decomposability and observability.
Precisely. It guarantees that the things we measure are real, observable quantities, not, fleeting imaginary weirdness.
And crucially, that complex systems can be broken down into independent, understandable parts. It's less a clever math trick and more like, reality's inherent operating system, maybe its foundational grammar.
Which naturally leads us directly into today's big question. If self-adjointness defines that stable frame, if it's the cosmic source code, then what's actually running inside that frame?
What are the programs? What are the actual processes, the dynamic engines that operate within that fundamental structure to give us, everything we see and experience?
You mean from the dance of atoms to the complexity of life itself?
Exactly. All of it.
And that, dear listeners, is what this deep dive is all about. We're calling it operator theory of everything. 5 codes, 1 cosmos.
It sounds incredibly ambitious, I know, and maybe it is.
Yeah.
Our grand mission today is to trace what we're calling these 5 fundamental engines or subroutines through an astonishing breadth of human knowledge. We're talking over 50 different fields.
50. That's a huge claim. So you're talking from quantum mechanics, the very rules of matter and energy.
All the way to things you might not expect. Ethics, information theory, biology, sociology, economics, and well beyond. We're shifting our focus from the underlying structure, that abstract self-adjoint operator, often symbolically represented as
H.
Right.
What's the H?
The meaning it generates, the actual behaviors it allows, the specific eigenstates it manifests. It's about trying to understand the language the universe is speaking through this structure.
Okay, so what are these 5 concepts, these skeletons or metaphysical primitives, as you put it?
So we see them as flow, invariance, symmetry, collapse, and bifurcation. And we're arguing they aren't just neat mathematical ideas. isolated concepts.
Yeah, we believe they're more fundamental than that. They're like the basic building blocks of reality's dynamic processes.
They are the core computational skeletons, maybe, that dictate how reality unfolds.
And the overarching reason we're embarking on this deep dive, the mission behind it all, is to understand why we as humans often fail to see what's truly happening in the world, why we misinterpret or struggle to predict complex phenomena.
Right. And perhaps, just perhaps, how we can begin to fix that, how to see more clearly structure by structure, operator by operator.
It's like we're performing an epistemic incompleteness audit across all these different disciplines.
An epistemic incompleteness audit. That's a powerful phrase. Can you elaborate on that a bit?
Absolutely. Think of it like a diagnostic toolkit for human knowledge. We'll explore how you could potentially look at almost any field, from hard sciences to social sciences, government policy, maybe even something as complex as human relationships.
Okay.
And ask, which of these 5 fundamental engines or codes is maybe missing here? What essential mathematical principle is being ignored or maybe underutilized that might be causing instability, unpredictability, or just a lack of insight?
That's a truly profound lens to view knowledge through. It's about spotting the blind spots in our understanding, isn't it? Seeing where we're maybe missing a piece of the underlying logic.
Precisely. It's about using what might be the universe's own operating manual to understand where our current frameworks might be incomplete.
Okay, I'm ready for this. This sounds huge.
Me too. Settle in, everyone. This is the deep dive.
All right, so self-adjoint operator H, it prevents everything from just being an irreducible, undifferentiated blob. It keeps popping up, doesn't it?
It really does. Quantum physics, classical physics, data analysis, AI learning. The concepts of stability, structure, and the ability to decompose complexity seem to always trace back to this elegant mathematical concept.
It really feels like a universal architectural principle, a bedrock, for any system that seeks to be stable and comprehensible.
Okay, now we unpack those 5 fundamental codes you mentioned earlier: flow, invariance, symmetry, collapse, and bifurcation. You're calling these realities subroutines.
That's the idea. These 5 concepts, these metaphysical primitives as we see them, all ultimately stem from or are deeply related to the master principle of self-adjointness. They're like the core engines or programs running within that stable framework.
And you're connecting them to really profound concepts: flow with time, invariance with truth, symmetry with beauty, collapse with choice, and bifurcation with life itself.
Exactly. We see them as the fundamental computational skeletons, the minimal blueprints for how reality behaves and evolves dynamically. Let's take them one by one.
All right. Code number 1, symmetry. You link this to beauty.
Yes. Symmetry, in this context, is about the universe's underlying design principle. How complex systems often have an inherent, simple, stable structure beneath the surface. It's about harmony, elegant patterns, compressed coherence.
And the math behind it.
This directly connects back to the mathematics of symmetric matrices and the spectral theorem we just discussed. The ability to find those stable, orthogonal eigenvectors.
And an example in action.
Think back to principal component analysis, PCA. It finds the hidden, stable axes, the principal components, in noisy, chaotic data sets by analyzing the symmetric covariance matrix. It reveals a kind of simple beauty, an underlying order hidden in the noise. More broadly, from the hexagonal symmetry of snowflakes to the spiral patterns in galaxies, beauty often reflects this kind of compressed coherence and robust underlying order that symmetry provides.
Okay, makes sense. Code number 2, invariance. You link this to truth.
Invariance is about the universe's bedrock. The rules, quantities, or properties that remain unchanged, regardless of your perspective or some transformation. It provides consistency, predictability, logic, the truths that hold no matter what.
And the math here.
This is deeply connected to Noether's theorem, a cornerstone of modern physics. It states that for every continuous symmetry in the laws of physics, there's a corresponding conserved quantity.
Like rotatiometry leading to conserved angular momentum.
Precisely. And the operators representing these conserved quantities, like momentum, energy, charge, have a special relationship with the Hamiltonian. They commute with it, meaning the order doesn't matter. This relationship is often guaranteed or made well-behaved by the self-adjoint nature of the operators involved. Self-adjointness ensures these fundamental conservation laws, these invariances, hold properly.
So an example, you mentioned the ice skater.
Right. Rotational symmetry implies conservation of angular momentum. When an ice skater pulls their arms in, they reduce their moment of inertia, and to conserve angular momentum, they have to spin faster. That conservation law, that invariance, is a direct consequence of the underlying rotational symmetry of space underpinned by these mathematical structures.
Got it. Code number 3, flow, linked to time.
Flow represents the universe's pulse, the engine of change. It's about how reality evolves smoothly, continuously, and predictably over time. Think Heraclitus. Everything flows. Crucially, it also ensures that probabilities don't break down during this evolution.
And the math. We touched on this earlier.
Yes, this is where unitary operators and Stone's theorem come back in full force. Remember, Stone's theorem guarantees that the generator of any continuous probability-preserving flow must be a self-adjoint operator. It's a mathematical necessity for probabilities to be conserved over time.
And the example, the Hamiltonian again.
Exactly. The Hamiltonian operator in quantum mechanics, being self-adjoint, generates the unitary time evolution. This guarantees that quantum systems evolve smoothly and probabilities are conserved. It ensures matter is stable and doesn't just vanish or probabilities go haywire. Without it, as we said, total chaos. It guarantees consistent flow through time.
Okay. Code number 4, collapse. You link this to choice. This sounds very quantum.
It is deeply rooted in quantum mechanics, but the principle might be broader. Collapse is the universe's decision maker in a sense. It's how the fuzzy, probabilistic quantum world full of superpositions of possibilities yields a single definite reality upon observation or measurement.
Turning quantum maybe into classical is?
Precisely. And the mathematical engine for this, projection operators. When you perform a measurement corresponding to a particular observable, a self-adjoint operator, the system's skate vector is projected onto one of the definite eigenstates of that operator.
And these projection operators.
They are themselves self-adjoint. The act of measurement uses a self-adjoint projection to force the system out of superposition and into a single definite outcome, effectively making a choice among the possibilities.
The classic example being?
The double slit experiment.
Okay.
Before measurement, the particle exists in a superposition of going through both slits. But when you measure which path it took, its wave function collapses, and it definitively chooses a single path. Projection operators are the mathematical machinery for that transition from possibility to actuality.
Okay, final code. Code number 5, bifurcation, linked to life or maybe creativity.
Yes, bifurcation is the universe's creative engine. It's about branching, splitting, the emergence of new structures, new patterns, often from seemingly chaotic or simple states. It's how systems transition qualitatively from one type of behavior to another.
And the math.
This involves bifurcation theory and catastrophe theory. These study how the stable states, the equilibrium points or eigenstates, of a system change as you vary a parameter. At critical points, stable states can suddenly appear, disappear, or split into multiple new stable states, creating new pathways for the system's behavior.
And self-adjointness plays a role here.
The analysis of the stability of these states often relies on examining the eigenvalues of operators related to the system's dynamics near the equilibrium points. Self-adjoint principles frequently underpin the methods used to determine whether these states are stable and how they might split or merge.
An example of bifurcation.
Think of a simple predator-prey model in ecology. If you gradually increase the food supply for the prey, the system might initially settle into a stable equilibrium with constant populations. But beyond a certain threshold, that stable point might become unstable, and the system bifurcates into a state of oscillating populations, booms and busts. That sudden change in behavior, that emergence of a new dynamic pattern, is a bifurcation. It allows for complexity, diversity, evolution. The tree of life itself is a grand bifurcation diagram.
Flow, invariance, symmetry, collapse, bifurcation. 5 fundamental engines, all tied back to self-adjointness. That's a powerful framework.
We think so, and it leads directly into part 3, using this framework as a kind of diagnostic tool.
Right, the epistemic X-ray. Explain that concept again.
The idea is to use these 5 codes as a kind of audit toolkit for human knowledge. It allows us to look at almost any field, economics, sociology, psychology, urban planning, you name it, and ask a critical question.
Which of these 5 fundamental codes are they potentially missing or underutilizing? Where is the mathematical logic of, say, flow or symmetry not fully integrated into their models or theories?
Exactly. And the hypothesis is that the absence of one or more of these codes often indicates where a field struggles with instability, unpredictability, paradoxes, or just a general lack of deep understanding. It points to where the blind spots might be.
And potentially where the next breakthroughs are hiding.
That's the exciting part. Can we use this to pinpoint areas ripe for innovation? The sources we looked at actually tried to map this out across dozens of fields.
Okay, give us some examples. Where are these engines supposedly missing?
Well, for flow time, The argument was it's often underrepresented in fields like digital humanities or even some areas of cryptography, which can sometimes treat information or texts as static artifacts rather than dynamic, evolving systems.
Interesting. What about invariance, Truth?
Suggested as potentially missing or weakly modeled in areas like food science, lacking universal principles across cuisines, or models of political polarization, struggling to find stable underlying truths or conserve quantities amidst the chaos.
Okay.
Symmetry, beauty harmony.
Pointed out as often lacking in fields like urban planning or supply chain logistics, are we building cities and systems without fully leveraging the mathematical principles of harmony, balance, and optimal structure that symmetry provides?
That's provocative. Collapse choice.
Argued as largely absent in fields like additive manufacturing, 3D printing, or maybe even aeronautics. These fields deal with bringing possibilities into reality, but perhaps lack a formal language for representing and reasoning about that collapse, from design space to physical object, or from potential flight paths to the actual trajectory.
And finally, bifurcation, life creativity.
This one was seen as almost entirely absent in surprising areas, like quantum computing, often focused on unitary evolution, less on the emergence of qualitatively new computational states, or educational pedagogy. Are we designing learning systems that account for and even encourage those sudden aha moments, those bifurcations in understanding?
So this isn't just about critique. The X-ray is meant to provide actionable insights, right? A roadmap for progress.
That's the goal. It's trying to suggest specific mathematical tools or concepts inspired by these 5 codes that could lead to breakthroughs if applied in fields where they're currently missing.
Like what? Give us some concrete examples of potential future directions.
Okay, so for flow, maybe using quantitative flow metrics, like those from fluid dynamics or network theory, to measure the vitality or dynamism in soft domains like sociology or literary analysis.
Injecting invariance.
Perhaps introducing gauge-style invariance models, things like covariant embeddings or homotopy-based text metrics, concepts borrowed from physics and topology into the humanities and biosciences to find deeper, more robust patterns.
Using symmetry.
The suggestion is to introduce harmonic or group spectral methods into areas like food science, predicting flavor pairings based on underlying symmetries, urban analytics, finding optimal city layouts, or digital humanities, discovering hidden structures in texts. Expect novel taxonomies and predictive models.
What about applying collapse?
Maybe prototyping collapse-aware user interfaces or architectural designs that explicitly anticipate and manage irreversible user choices or branching pathways. Thinking about how possibilities become locked-in realities.
And exploiting bifurcation.
Fields like neuroscience, virtual reality design, or educational pedagogy could potentially exploit symmetry-breaking order parameters, mathematical tools for identifying and triggering transitions between stable states to deliberately induce desired shifts in brain activity, user experience, or student understanding.
So using the mathematics of symmetry for new flavor pairings or bifurcation to design educational programs that anticipate and encourage those aha moments, it's about transferring these fundamental mathematical logics.
Exactly. It's a framework for potentially predictable scientific revelation guided by the universe's own core operating principles.
Which brings us, inevitably, to the deepest mathematical challenges themselves, the Millennium Prize Problems. You're suggesting a profound link between these 5 codes and those million-dollar questions.
Yes, the sources propose a fascinating mapping. The idea is that each of the major Millennium problems can be viewed as probing the mathematical limit, the ultimate boundary, of its corresponding code or skeleton. They represent spectral resistance points in the fabric of mathematics.
So solving them isn't just about the math, it's about grasping the ultimate limits and possibilities of reality as described by these codes.
That's the perspective. Let's map them out.
Okay, Navier-Stokes equations. These describe fluid flow. Which code does that link to?
Linked to flow energy. The problem challenges our ability to prove the existence and smoothness of solutions, essentially tracking nonlinear propagation of energy and momentum at infinite resolution. It's about the ultimate nature of continuous change and dynamic flow.
Makes sense. Next, the Yang-Mills existence and mass gap problem. This is from particle physics.
Linked to mu errors. Local invariance. This problem probes whether the principles of local gauge invariance, a powerful symmetry principle in physics, can actually generate mass from a massless theory. It's about the emergence of structure, mass, from fundamental symmetries and unchanging rules, the heart of invariance.
Then the big one we discussed earlier, the Riemann hypothesis.
Linked to V-area symmetry plus spectra. It directly questions whether the spectral harmony, The eigenvalues of the primes, via the zeta zeros, is fully countable and perfectly aligned. It's the ultimate question about underlying symmetry and spectral order in the seemingly chaotic realm of numbers.
The P versus NP problem. This is about computation, the difficulty of finding solutions versus checking them.
It's linked to collapse infobound, PVS-NP, pits, knowing, checking a solution, P against finding, searching the possibility space, NP. This is described as the very soul of collapse, the fundamental difficulty or cost associated with reducing a vast space of possibilities down to a single actual solution. It's about the limits of turning maybe into is.
And finally, the Hodge conjecture. This is from algebraic geometry.
Linked to Touche, order param SB bifurcation. This conjecture asks whether certain types of emergent geometric order, algebraic cycles, always reflect a hidden, simpler underlying shape, topological cycles. It's about how new complex structures emerge and whether they faithfully represent simpler origins, connecting deeply to bifurcation, symmetry breaking, and the emergence of order.
Wow. Viewing the Millennium Problems through this lens, it makes them seem less like isolated puzzles and more like fundamental stress tests of reality's core operating principles.
Exactly. When you see it this way, the universe starts to look less like a collection of disparate laws and more like a single unified computational process,
A process built on 5 core programs.
all powered by the master logic of self-adjointness. We can perhaps break down the why into a few key recurring reasons that keep coming up.
Okay, reason 1. Laid on us.
Reason 1. Geometry often naturally implies self-adjointness. As we saw with the Riemann hypothesis example, stable geometric structures or spaces designed to capture fundamental properties often come with natural operators like the Laplacian that are inherently self-adjoint. If you build stability into your foundational structure, self-adjoint dynamics often follow as a natural consequence.
That makes a lot of sense. Stable structure leads to stable dynamics. Okay, reason 2.
Reason 2. Self-adjointness guarantees stability through real values. This is absolutely fundamental. We've hit this a few times. It prevents systems from having core, measurable properties described by imaginary numbers.
Which just wouldn't make physical sense.
Right. It keeps things grounded in physical reality, ensuring stable energy levels, stable frequencies, and preventing unphysical behavior like particles spontaneously appearing or disappearing.
Okay, reason 3.
Reason 3. It guarantees decomposability through orthogonal eigenfunctions, the ability to break complexity down into understandable parts.
This seems huge for us humans trying to understand things.
This is perhaps the most practical consequence for human understanding. It allows us to analyze intricate systems, whether a complex signal, a quantum state, or a massive data set, by breaking them down into a sum of simple, independent, stable modes or building blocks. It is the mathematical foundation for spectral analysis and, by extension, much of modern science.
Making sense of the whole by understanding its parts.
Exactly. Reason 4 seems more practical for us humans. Computability.
Ah, yes. Can we actually calculate these things?
Exactly. The fact that self-adjoint operators, when discretized, lead to symmetric or Hermitian matrices is a massive boon computationally. We have incredibly robust, stable, and accurate numerical algorithms specifically designed to reliably find the eigenvalues and eigenvectors of these matrices. We can actually compute the answers and trust them.
Which is pretty important if you want to test these ideas. Okay, and maybe the deepest reason, something that emerged strongly from the Riemann work but seems much more general.
Reason 5. Self-adjoint operators act as the universal engine for balancing fundamental opposing forces. This feels incredibly profound.
A cosmic balancing act? What forces?
Think of it this way. On one side, you often have terms in the operator, like the Laplacian part, that represent diffusion. The tendency to spread out, to smooth over, to homogenize, to increase entropy, like ink spreading in water.
So the universe's inherent tendency towards featurelessness, towards equilibrium, towards heat death, eventually.
Precisely. On the other side, you have the potential term Vx, like the one in the Schrödinger equation or the Riemann operator. This represents an identity force, a force that creates barriers, establishes structure, maintains distinctions, preserves information, and resists that homogenization.
Like the force is holding an atom together, or maybe the unique identity of each prime number resisting being averaged out.
That's the intuition. So it's this constant tension, the universe wanting to spread out and lose structure versus the universe wanting to maintain distinct structures and information.
And the self-adjoint operator finds the balance point.
That's it. And the eigenfunctions, the stable states, the combined self-adjoint operator, the diffusion part plus the identity part, are the equilibrium points. They're the stable compromises where these two fundamental opposing forces are in perfect persistent balance.
That feels like more than just physics.
It feels like a fundamental principle of information, or even of existence itself. Any system that needs to persist stably, any information that needs to endure must find this delicate balance between merging and separating, between entropy and structure. The self-adjoint operator is the mathematical machine that finds and enforces these stable equilibrium states.
And that connects back to that intriguing idea you mentioned, computational time dilation.
It does seem deeply related. The identity force, the potential Vx, acts like a barrier that prevents distinct states or entities from simply collapsing into the background noise of diffusion. Maintaining this distinctness against the homogenizing pressure requires something, perhaps call it computational effort or energy. This effort, this resistance to homogenization, might be experienced as a kind of cost or delay, a kind of computational time dilation.
So stability isn't static, it's a dynamic equilibrium.
Maintained by this balance, which the self-adjoint operator mathematically enforces consistently over time.
So wrapping up this incredible journey, the self-adjoint operator, it's not just a tool we invented. It feels more like an inherent architecture, a fundamental blueprint for reality.
Exactly. A fundamental blueprint for any system, anywhere, that needs to be stable, measurable, and decomposable into understandable parts. Its unreasonable effectiveness might simply be because these properties, the reality of core values, the orthogonality leading to decomposability, the stable balance of opposing forces, are the absolute prerequisites for any kind of comprehensible, persistent reality to exist at all.
For information to be processed, for structure to endure.
For anything like a universe to happen.
So maybe we didn't invent it so much as we discovered it as the only possible logic that allows for a universe like ours to be.
It really starts to feel that way, doesn't it?
It seems to be this common thread.
It suggests that stability, truth, beauty, choice, and life are not just philosophical ideals. They are the direct mathematical consequences of a universe that must be stable and comprehensible to exist at all.
And the Millennium Problems are not just abstract puzzles. They are the final frontiers of our understanding of each of these cosmic engines. Solving them isn't just about winning a prize, it's about grasping the ultimate limits and possibilities of reality itself.
Wow, what an absolutely incredible journey today. We truly hope this deep dive has given you, our listeners, a new appreciation for this mathematical structure that so profoundly shapes our world.
From Austin, Texas, this is SpaceTime Cafe. Stay coherent.
And stay curious.